Welcome to Shanti-Peace for Mathematics. In this lecture, we are going to discuss regarding the power series and a taste for conversions for the power series. It is very different type of series because it's involved the variable x. So a definition of power series is defined like this. If you have any series of the form un, summation of un x minus a power n, where this x is a variable which we have here is a variable. Un is a sequence and that sequence is known as a sequence of coefficient of the series and a is any constant number. And this is called the power series about a, or it's also known as just a power series. One should note that a power series is a function of x and which make it different from other series so far we have discussed. So far we have discussed about this series which will involve the positive term series or alternating series or any kind of series we have. But that series which we have discussed, it is not a function. Here this is a function of x. And so the power series are always consistent of a variable along with the number. Since the power series is a function of x, the convergence of the series depends on the value of x, whether the given series is convergent series or it is a divergent series. That is, if we define a function f of x is equal to summation n running from 0 to infinity un x minus a power n, then the domain of f is the set of values of x for which the power series is convergent. So it's kind of such things is there, that is, if f of x, whatever the domain of this function f of x is there, and when I say it is equal to, it is not actually equal to, whenever this series is converged to that function, that is known as a convergence of function. For example, you probably have learned about some very well-known series which you have come across with. For example, e power x. You know that the series of e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial up to so on. So this is actually a power series, and for what value of x this power series will converge to e power x. E power x is a function that we know. So for what value of x this power series will converge to e power x. Similar way, you have a series of sin x and cos x, might be you have studied in your mathematics subjects or in physics or in chemistry. Such power series are very useful and it will appear in many a times. So it is interesting to know that for what value of x this power series is convergent and for what value of x it will be divergent. So also note that since a is constant and for x is equal to a we have, that means if I substitute the value of x as a, we'll have summation of n running from 0 to infinity un into a minus a raised to n, because we have substituted here the value of x which is a. We'll have this. So this will give me summation n running from 0 to infinity un into 0 power n. But 0 power n will be gives me 0, so that means it is 0. So f of a is a 0 which is a finite number. Thus the power series is always convergent for x is equal to a. That is the first things we can say from this. Thus a power series always converges for x is equal to a. And the domain of f is known as interval of convergence. So whatever the domain of this function is there, that means for whatever the value of x this power series is convergent, that all values if you put together, and that is known as interval of convergence. Now we have very well-known theorem on this power series and will not discuss a proof for that, and that is a test for convergence of power series, which states like this: the power series summation n running from 0 to infinity un x minus a raised to n is convergent for either, so any of these three will be possible, either for x is equal to a only, or the interval a minus r to a plus r, that is mode of x minus a less than r, for some r where x possibly include both endpoints, and here r it's called radius of convergence. So this is also a definition of radius of convergence. This r is called the radius of convergence. And the third one, or the set of all real numbers. So any one of the three conditions will be possible. That means this power series is only converged for x is equal to a, or it will be converged for some interval which is of this form a minus r to a plus r, or it will be converged for all the real numbers. In case 1, here we can say that the radius of convergence is 0. That means the value of r here it is 0. And in this case the radius of convergence is infinity. So here you have r0 and here you will have r infinity. And here whatever the length of this interval will have by 2. And that is called the radius of convergence. So let us try to solve some of the examples which are based on this power series. The proof we have not discussing here. So the first example that we have already discussed, that find the interval of convergence of the series summation x raised to n upon n factorial, where n running from 0 to infinity. As we have seen that this is exactly the series which we have talked just before few minutes, that is the exponential. This is a series of exponential series. Here we'll consider whole this value as an, that is x power n upon n factorial, and we'll use a ratio test for checking with whether this series is convergent or not. So we use the absolute ratio test. So for that we'll see what is a n plus 1. We know that it is x power n plus 1, and to see what is the ratio test and its example, the video is already prepared for that. You can go to the I button and you can see what is the ratio test and what will be the root test. So now we'll check what is the limit of a n plus 1 upon a n, but its modulus, because we are using here the absolute ratio test. So that is limit of x power n plus 1 upon n plus 1 factorial into x raised to n. In the denominator we will have n factorial, which goes in the numerator, so we will have n factorial in the numerator as n tends to infinity. So this will gives me, you just observe that this x raised to n will get cancelled out, only x is left in the numerator, and this n factorial will cancel out, so here only left is n plus 1. So the left quantity is x upon n plus 1, and since n tends to infinity, 1 upon n plus 1 will tends to 0, that we know, and mod x is constant with respect to n, so I'll take outside, so it is mod x into 0 we have, so that will give me 0, which is less than 1. That means the series is converged for all x, hence the given series is converged for all x, and therefore the interval of convergence is r, set of all real numbers. And what is the radius of convergence? And the radius of convergence, that is r, is infinity. As we have discussed in the previous case in the theorem, if it is radius or the convergence, this power series is converged for all real number, then the radius of convergence is infinity. So here we have the radius of convergence is infinity, and the interval of convergence is a set of all real numbers. Let's solve another example. The question is, find the radius of convergence and interval of convergence of the series summation n running from 0 to infinity n cube into x minus 1 raised to n upon 5 raised to n plus 1. So here is also we are using the absolute ratio test to find out the radius of convergence for this solution. We use the absolute ratio test. Here we have an. We'll consider whole this quantity as an. It is n cube x minus 1 raised to n upon 5 raised to n plus 1. So a n plus 1 will gives you n plus 1 cube x minus 1 raised to n plus 1 upon 5 raised to n plus 2. Now we'll check what is the limit of the ratio, that is a n plus 1 upon a n, but it is in modulus because we are using the modulus absolute ratio test. This will be limit of, we'll write first what is the value of a n. The value of a n is this, that will substitute, that is a n plus 1 power 3 x minus 1 raised to n plus 1. The denominator will have 5 raised to n plus 2. The value of an, that is n cube x minus 1 raised to n, and the denominator will have 5 raised to n plus 1, that I will write in the numerator 5 raised to n plus 1. You just observe that this x minus 1 raised to n will get cancelled out. Only x minus 1 is left. This 5 raised to n is also cancelled out, n plus 1. Only 5 left here. Here it is x minus 1 left. And this is as n tends to infinity we need to calculate. So that's why it is limit mod of x minus 1 into n plus 1 whole cube as n tends to infinity. This is upon 5 left. This is equal to limit of mod of x minus 1 by 5 as it is. And if I divide this n in the numerator and the denominator, then we'll left with 1 plus 1 by n upon 1 power n as n tends to infinity, and we know that as n tends to infinity 1 upon n will tends to 0, so this will gives me 1. So the finally the left is x minus 1 upon 5. And we know that in the ratio test, if this limit is less than 1, then the series is convergent. So that means if this is less than 1, then we say that the series is convergent. So I can say that, therefore, if mod of x minus 1 is less than 5, that is exactly the situation we have written here by multiplying 5 both the sides. The series summation n cube x minus 1 raised to n upon 5 raised to n plus 1 is convergent. And if you compare this with this situation, that is mod of x minus a, here the value of a is 1 and r is, we got 5. So therefore the radius of convergence is 5. So from this what we can say, therefore the radius of convergence of the series is 5. Now we need to find out what will be the interval of convergence. To see the interval of convergence, let us expand this modulus. So now mod of x minus 1 less than 5 gives minus 5 less than x minus 1 less than 5. So this will implies that if I add 1 in this inequality, then it is 1 minus 5 less than x less than 5 plus 1. So that's why this will implies 4 minus x less than 6. Now we need to see what will be the behavior of this series at x is equal to 4 and at x is equal to 6, and that will gives you your interval of convergence. So now for x is equal to 4, the given series summation n running from 0 to infinity n cube x minus 1 raised to n upon 5 raised to n plus 1 will be summation n running from 0 to infinity. If I put n equal to x is equal to 4 here, it is 4 minus 1, so it is n cube into 3 power n upon 5 power n plus 1. Now we have to check that whether this series is convergent or not. So for that I will consider Bn is equal to n cube into 3 power n upon 5 power n plus 1. We'll use the ratio test to check the convergence of this series, that is limit of bn plus 1 upon bn as n tends to infinity will implies limit of n tends to infinity. This is a positive term series, so there is no need to take the modulus here. It is n plus 1 cube into 3 raised to n plus 1 upon 5 raised to n plus 2, and into bn upon bi is there, so that's why it is n cube into 3 power n and upon 5 raised to n plus 1. So you will have 3 power n is cancelled out, left with 3. 5 power n plus 1 is cancelled out, left with 5. So we'll have the answer is left is 3 by 5 into limit n tends to infinity n plus 1 upon n whole cube. And if I divide numerator and denominator by n in this inside this bracket, so we'll have 3 by 5 is the answer. Let me write one more step here. Will gives me 1 plus 1 by n upon 1 whole cube. So the finally it will be 3 by 5 is the answer, which is less than 1. 3 by 5 is less than 1. So for x is equal to 4, the given series is convergent. Therefore, series summation n cube into x minus 1 raised to n upon 5 raised to n plus 1 is convergent for x is equal to 4. Now for x is equal to 6, we have to check. For x is equal to 6, the given series n cube into x minus 1 raised to n upon 5 raised to n plus 1, n running from 0 to infinity, will reduce to n running from 0 to infinity n cube. So here the x is 6, so it is 5 raised to n upon 5 raised to n plus 1. That will give me 1 by 5 summation n running from 0 to infinity n cube, because 5 raised to n will get cancelled. And this I can write down 1 by 5 summation 1 upon n raised to minus 3 n running from 0 to infinity. This is divergent. Why this is divergent? By p test, because the value of p here it is minus 3, which is less than 1. As you know that in the p test, if the value of p in summation n raised to p, if it is greater than 1, then it is convergent, otherwise it is divergent. Therefore, the series summation n cube x minus 1 raised to n upon 5 raised to n plus 1 is divergent for x is equal to 6. Therefore, now we conclude that the interval of convergence is have the interval to 6, but in 6 it is divergent and for 4 it is convergent, that we have concluded. So the interval of convergence will be close 4 to open 6. Let's solve one more example here. The example number 3. Interval of convergence of the series n running from 0 to infinity n factorial into 5x plus 1 raised to n. Here also we are applying the absolute ratio test to check whether what will be the interval of convergence. We use absolute ratio test. Here we have an which we have calculated, it is n factorial into 5x plus 1 raised to n. Therefore, if you check an plus 1 will be n plus 1 factorial into 5x plus 1 raised to n plus 1. Now, limit of an plus 1 upon an as n tends to infinity will gives me limit of n factorial is this value, that is n plus 1 factorial into 5x plus 1 raised to n plus 1, and n is n factorial into 5x plus 1 raised to n as n tends to infinity. Just observe that this 5x plus 1 will cancel with this one, left with 5x plus 1, which is independent of n, so I'll write down outside. And this n factorial will cancel with n plus 1 factorial and left with n plus 1. Quantity is left, which is 5x plus 1 with the modulus. So I'll just apply the modulus here. Is modulus of 5x plus 1 limit n tends to infinity n plus 1, which is positive, so not writing modulus there. As n tends to infinity, this will be infinitive. So this will gives me infinitive. Hence, we can say is series is divergent for all value except 1, that is x is equal to a, which we have minus 1 by 5. Hence, the given series is divergent of all value x except x plus 1 equal to 0. This x is equal to 1 by minus 1 by 5. Therefore, the radius of convergence equal to 0 and interval of convergence equal to minus 1 by 5. Only a one point, singleton point you will have minus 1 by 5. Let's solve one more example. One. Examining for what value of x is square by 2 minus x cube by 3 plus x raised to 4 by 4 minus x raised to 5 by 5 up to so on is convergent. Here we consider our an, that you can just see that it is an alternating series, that is first term is plus, second one is minus, plus minus, so it is alternating series. I will say it is minus 1 raised to n plus 1. It is x power, it starts with 2, so I will say it is n plus 2 or n plus 1 upon n plus 1, n running from 1 to up to so on. I am using the absolute ratio test. Now see what is limit of mode of an plus 1 upon an as n tends to infinity. That will gives me limit of mode of an plus 1. So we have it as minus 1 raised to n plus 2 x raised to n plus 2 upon n plus 2. Here we have a and it is minus 1 raised to n plus 1 into x raised to n plus 1 in the denominator n plus 1 will goes in the numerator, will have n plus 1. We just observe that this x raised to n plus 1 is cancelled with this one, it is left with x. This will cancel with this one, it is left with minus 1, but due to this modulus this minus 1 is also gone away. So hence we will have limit of x upon x mode of x into n plus 1 upon n plus 2 as n tends to infinity. But mode is independent of n, so I will write down outside, and if I divide the numerator and the denominator by n, we will have 1 plus 1 by n upon 1 plus 2 by n. So finally the mode x should be the answer, because it is 1 plus 0 upon 1 plus 0 as n tends to infinity. Mode x is the final answer we have. And we know that if the mode x is less than 1, then by ratio test we will say that it is convergent, and for mode x is greater than 1, we will say it is divergent. We need to see what will happen at the end points. Thus, if mode x is less than 1, then the series minus 1 raised to n plus 1 x raised to n plus 1 upon n plus 1 is convergent. So I can say that the radius of convergence is 1, because the value of r is 1 here. Now we need to check, because we need to, if I can expand this one, this is minus 1 less than x less than 1 we have. So we need to check what will happen at the end point. That means if x is equal to 1, what is the situation of this series, and what will happen if x is equal to minus 1. Now for x is equal to 1, let us see what will be this series. Here the series is summation minus 1 raised to n plus 1 into x raised to n plus 1 upon n plus 1 will convert to summation minus 1 raised to n plus 1 upon n plus 1, and running from 1 to infinity. So x is 1, will substitute here, and this is the alternating harmonic series which we have. So this is, since it is an alternating series, we need to apply the Leibniz test to test whether this series is convergent or not. To see what is the Leibniz test, you will go to the I button, you can see what is the Leibniz test. It is the test for convergence of alternating series. Already video is available, you can go to the I button and see. That we need to see the 3 conditions should satisfy. I will say comparing this equation with the series minus 1 raised to n plus 1 upon plus 1 summation minus 1 raised to n minus 1 into bn will have bn is 1 upon n plus 1. And as we know that Bn is greater than 0 for every n, as n plus 1 is always greater than n, 1 upon n plus 1 is always less than 1 upon n for every n. This is true. Therefore, the Bn is decreasing sequence, and a limit of Bn as n tends to infinity is 0. So therefore, this series is satisfying all the conditions of Leibniz test. So by Leibniz test, minus 1 raised to n plus 1 upon n plus 1 is convergent. So for x is equal to 1, it is convergent. Let me check what will happen for x is equal to minus 1. X is equal to minus 1 is minus 1 raised to n plus 1 into x raised to n plus 1 upon n plus 1 is equal to summation n running from 1 to infinity. So it is x is equal to minus 1. So we will have minus 1 raised to n plus 1 into minus 1 raised to n plus 1 upon n plus 1 will gives me summation of n running from 1 to infinity 1 upon n plus 1. It is divergent. P series test. Because here the value of P it is 1. Therefore, the interval of convergence is for minus 1 it is not convergent, and for 1 it is convergent. So that means it is this. So it is the open interval minus 1 to close interval 1 is your interval of convergence, and the radius of convergence is 1 for this example. That's it for this video. Thank you for listening me. If you like this video, please press the like button. If you have any comment, suggestion or question, please drop down in the comment box below. See you in next video. Till then, bye bye. Sayonara.